All right, this is Honors Algebra 2 Pre-Calculus. We're doing 12.5 in Algebra 2, which is binomial distributions. So we do things a little bit out of order in this class because we take some things that we would normally cover in Algebra 2 and we cover them in Pre-Calc because the Algebra 2 and Pre-Calc books have a lot of overlap in the textbook, and we do both courses in a single year in this block course. So what that means is occasionally we will stumble across something that you would have seen earlier in Algebra 2 book, but because we do it in the Pre-Calc section of the course, you haven't seen it yet. This is that. So let's talk about some stuff that you're going to need to know to do binomial distributions. So we haven't talked about probability really at all. You might have seen it in some of your science classes. It might have come up a little bit in Algebra 1 or geometry. But the theoretical probability of an event E can be written as P of E. And that's the number of favorable outcomes, meaning the number of things that we want to happen over the total number of outcomes. For example, if you're flipping a coin and you want to get tails, the probability of tails is a 1 out of 2. Meaning 50%, because there is one side that's tails and there's two total sides. So theoretically, you have a 1 out of 2 chance of getting tails. This is called theoretical probability because it's based on what should happen in a perfect world based on the number of items available, right? Experimental probability, and that's when you actually do an experiment and collect data, is the same concept, but instead of using what should happen, you use what actually did happen. When you flip the coin. So let's say you flip the coin 5 times, right? You're definitely not going to get a 50% probability if you flip the coin 5 times because 5 is an odd number and there were only 2 possibilities, heads or tails. So there's no way that it came up tails 2.5 times. That's not possible. So you flip a coin 5 times, you got tails 3 times, then the experimental probability of tails was 3 out of 5, meaning 60%, because you had 3 successes over the 5 attempts that you made at flipping the coin, right? So we're going to do a couple quick probability questions before we get into binomial distribution because, again, it's helpful to have a background in some minor probability things before we delve into this topic. All right, so you roll a 6-sided die 10 times, and here are your rolls, right? 1, 2, 5, 5, 3, 2, 6, 4, 5, 1. Based on your roll, find the probability, the experimental probability of each of these. So what's the probability that I get a 5? Well, I rolled this thing 10 times, and I got a 5 1, 2, 3 times. So 3 out of 10, or 30%, right? Now, it's worth noting that the theoretical probability would be 1 out of 6, right? Because one side of this 6-sided die is a 5, so the theoretical probability would have been a 1 out of 6, right? But here it's a 3 out of 10 because I got 5 more times than you would necessarily expect. What's the probability that I got an even number, the experimental probability, like based on my results? Well, I got a 2, a 6, and a 4. Those are my even numbers, so it seems 4 out of 10, or 40%. Now, if I were actually doing the theoretical probability, that's a 40, sorry. If I were actually doing the theoretical probability, right, in theory, it should be 3 even numbers out of the total 6 numbers, which would be a 50%, right? So just to be clear, the experimental probability is often not the same as the theoretical probability, and that's fine, right? The probability I get less than a 7. Well, every one of these numbers is less than a 7, right? Because there's no 7 on the die, and 6 is the biggest number. So that's 10 out of 10, or 100%, right? And that one is the same as the theoretical probability. The theory is also that, again, all 6 sides are smaller than the number 7, so that's also 100%. So sometimes the theoretical probability is the same as the experimental probability, but not always. And here, again, I only asked you for the experimental. I just wanted to compare and contrast the two. All right, so P1. You flip 2 coins at the same time. You do this 10 times and record your answers for your flips, like HT, where heads was the first coin and tails was the second, right? So here are your flips: HH, HT, TH, TT, TT, HT, HH, HT, TH, TH. Based on your roll, find each experimental probability. So you flip this thing 10 times, and I did pick 10 again because it's a nice friendly number. What's the probability that you got HH? And we're not actually going to do the theoretical one here because that's a little bit above our skill level to talk about what the odds are that you'd get HH. But in my experimental probability, it was 2 out of the 10 times that I flipped the coins. So that's a 20% chance. What's the probability I get mixed results? Well, what I mean by mixed results is the two letters are different, right? So 1, 2, 3, 4, 5, 6. That seemed to happen 6 out of 10 times, which would be 60%, right? And what's the probability that the first coin is a T? Well, first coin is a T. 1, 2, 3, 4, 5. So it seemed to be 50%, right? 5 out of 10 is 50%. So that's how probability works. It's favorable outcomes out of the total number of outcomes. And again, theoretical is when you're talking about what ideally should happen in the real world, like you get a 50% chance of flipping and getting tails. But experimental is what happens when you actually flip a coin, or when I give you fake data that says you flipped a coin and you use the data to answer. All right, so we'll need to walk through 2 more concepts, which we'll see again in pre-calc to understand the formula for binomial distribution. So let's go ahead and walk through them. First concept is called a factorial. So factorial is like really excited math because it's actually, the notation for a factorial is actually an exclamation point. Yay, factorial, yay! Yay, so exciting. All right, so for some positive integer n, and it does have to be an integer, you can't do like 2.3 factorial. It has to be an integer. For some positive integer n factorial, which we write as n exclamation point. So don't just say like n really enthusiastically. I mean, you can, but that's totally not what it means. It means n factorial is defined as n times n minus 1 times n minus 2 all the way until you get down to 1. It is also worth noting that, see how this says positive integer? So this is a special rule. 0 factorial is 1. You just kind of have to trust me on that, but that's a special rule that you should memorize. So memorize that 0 factorial is 1. So let me walk you through what I mean by this formula. 3 factorial, I start with the 3, and then I multiply by all the numbers until I get down to 1. So 3 factorial is 3 times 2 times 1, which is 6. 5 factorial starts at 5, and then I multiply by all the numbers until I get down to 1. So 5 times 4 times 3 times 2 times 1, which is 120. Okay, so that's 3 factorial and 5 factorial. There is a way to do this in your calculator, right? So in your calculator, if you go to math, and you go over to probability, and I'm pretty sure it's 4. 4 is the factorial symbol. So math over to probability, and then sure enough, there's 4. Now you'd have to put the number first. So I'm going to quit out for a sec. If I wanted to see what 3 factorial is, I'd put 3. I'd go to math over to probability and pick 4, and there's my 3 factorial. Boom, it's a 6. 5 factorial, I'd go 5, math over to probability and pick 4. There's my 120. Okay, so there is a way to do that in a calculator, although most of the time when we have smaller factorials, it's actually less work to do it by hand. Okay, so we're going to evaluate each factorial. We can certainly check it in a calculator. So 4 factorial just means 4 times 3 times 2 times 1, right, which is 4 times 6, or 24. 8 factorial divided by 6 factorial is actually kind of cool. This one's got a cheat, because if you think about what 8 factorial is, you could type it in a calculator. You get a pretty big number. But 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Now, if we were in regular class and I were talking to you, I'd be like, anybody see a thing that I can do? And somebody would chime in that because this is literally all multiplication and division, I have a factored expression I can cancel. I can cancel the 1s and the 2s and the 3s and the 4s and the 5s and the 6s, and holy cow, this is just a 56. All right? So that's a pretty cool trick with factorials, right? And then the third one, right, C, is going to be 2 times 1 times 3 times 2 times 1. That's going to be essentially a 2 times a 6, or a 12. It is worth noting that this is not 6 factorial. You can't, factorial comes before pretty much everything. Like, factorial comes before MDOS. The only thing that we do before a factorial would be if I gave you something like parentheses, like 5 minus 1 factorial, you would make 4 factorial, right? Factorial comes really early in this order of operations, right? So the factorial comes first, right? You can think about it like it's this, right? It means do all this first and do all this first. It's not a 6 factorial, okay? And again, we're going to touch on this again when we get to pre-calc, but I want to make sure you have a brief intro. So go ahead and take a second and evaluate the factorial. You can certainly check on the calculator. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. I happen to know that 5 factorial is $1.20 because I already did it. So 6 times $1.20 is a $7.20, right? I already know that this is $1.20. The 10 factorial over 7 factorial is that same trick, right? 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But I know the bottom has all of the 7 and below, right? Like the bottom starts at 7 and will have all those values. So, oh look, they all cancel. kind of missed, but you get the idea. So I end up getting 10 times 72, which is also a 720. Not intentional, but there you have it, right? 3 factorial times 3 factorial is 3 times 2 times 1 times 3 times 2 times 1, right? That's 6 times 6, or 36. It is worth noting that it is not 9 factorial. No, don't do it. It's not 9 factorial, right? You can't do that. You have to treat this as its own thing and this as its own thing, all right? Okay, so we needed to learn one more thing, and then you can make sense of this crazy thing that is actually supposed to be the point of this entire video. So combination notation. So if you have n items and you want to pick r of them, then there's a notation for that. It's called NCR, or N choose R. So you can read this as N choose R. That's how we can read that, N choose R. And that notation, it can also be written, so it can either be written as NCR or it can be written as N over R in parentheses like this, but it's not a fraction. There's no bar in the middle. But what it means is N factorial over R factorial and then N minus R factorial. There's a button that performs this action too, and I'll walk you through that in just a sec. But just to point out what I mean by this idea of you have n items, right? If you have n items and you're choosing r of them, this is like saying if you have, you're packing for a trip. I don't know, you're able to travel. The pandemic is over. It's glorious. So you're packing for a trip, and you have 5 shirts, but you realize that you can only pack 2 of them, right? So that would be an example of 5 shirts, but you can pick 2 of them. 5 choose 2. Right? And that's going to be something that comes up a lot when we talk about probability later in math and we talk about ways to count things. So if you had 5 shirts and you only wanted to pick 2 of them, the way that you would actually figure out how many different ways you could do that would be 5 factorial, because 5 is that n, so 5 factorial, 5 times 4 times 3 times 2 times 1, over the number you want to choose, which is 2 factorial, so 2 times 1. So here we go, 5 factorial, 5 times 4 times 3 times 2 times 1, over 2 factorial, because that's my r factorial, times n minus r, so 5 minus 2 factorial, which would be 3 factorial. And then we've already seen that I can actually simplify this pretty easily by myself, right? Without using a calculator, I can actually simplify by saying, oh, look, there's a 3 with a 3 and a 2 with a 2 and a 1 with a 1, right? So I'm going to get that this is 20 over 2, and I can pretty quickly get it to 10. There is a button to do this in your calculator. So just like we found the exclamation point for factorial under probability, if we go to math and we go over to probability and pick 3, we can get NCR. When you do that, though, just like we saw with the factorial, you have to put the first number first. So that if the 5 is the n, I have to type in 5, then get the NCR button, then type in the 2 and hit enter, and I'll get a 10. So again, we're going to spend more time on this notation and its significance and what it means when we get to the probability section in pre-calc. But for right now, what you need to know is that that's what this notation means. That's what NCR means. So let's go ahead and evaluate each of these by hand and on the calculator to verify that we know how to do it. So 10 choose 3 means you have 10 items and you're grabbing 3 of them, right? You have, I don't know, 10 notebooks and you get to grab 3 for your the start of the new school year or whatever, right? So it's going to be 10 factorial, right, n factorial, over r factorial, and then 10 minus 3 factorial. So this is going to be a 10 factorial over a 3 factorial and a 7 factorial. 10 times 9 times 8. Now, I'm not going to write everything below 7 because I recognize that 7 factorial is totally going to cancel. So you could actually kind of be lazy about this. And you could say, wait a second, this is the same as a 10 times a 9 times an 8 times. Instead of writing 7 all the way down, I'm just going to keep calling it 7 factorial. And I have a 3 times a 2 times a 1 times that 7 factorial. All of those terms, 7, 6, 5, 4, 3, 2, 1, they're all going to cancel. So I end up getting essentially, I could either make this a 720 over a 6, which is fine, right? I could do 720 over 6 and get that it's a 120. Or I could use the 3 to cancel the 9 and the 2 to cancel the 8, and I would still get a 120. So the answer is it's a 120. If I wanted to type this in my calculator, I would do 10, math over to probability and 3, and then I'd pick the number 3. And there's my $1.20. 5 choose 1 is going to be a 5 factorial over a 1 factorial, and then a 5 minus 1 factorial, which would be a 4 factorial. So I get 5 times 4 times 3 times 2 times 1. I didn't have to write that whole thing out. Because what I notice is that these guys are all going to cancel, and I'm just going to get 5. And that one actually makes logical sense if you think about what it means to choose items. You have five items and you're only picking one of them. There's only one way to do that. You could pick the first one or the second one. You know, there's only 5 options, so you have 5 different ways to pick. So it's 5. All right, so let's go ahead and try. You're going to try a P3, and then I promise we're going to get to the thing that is actually the topic of this section. So 8 choose 5 is going to be 8 factorial over 5 factorial, and then 8 minus 5 factorial, so 3 factorial. Again, I'm going to argue that the biggest factorial on the bottom is a 5, so I'm not going to write the 8 all the way down. I'm going to write 8, 7, 6, and then I recognize that everything below 6 is going to cancel. And then I have a 3, 2, and a 1. So the 5 factorial is going to cancel with the 5 factorial. Conveniently, 3, 2, and 1 is a 6, so I think I just get that this is a 56. And I can check that by doing, if you want, you can actually just hit second enter, because that's probably faster now. And I can do 8, NCR 5, and there's my 56. 11 choose 6 is going to be an 11 factorial over a 5 factorial 6 factorial. Oh, I did that backwards. 6 factorial, 5 factorial, but it doesn't really matter. So r factorial and n minus r factorial. Now this one's going to be a bit of a pain. The closer together the two bottom numbers are, the longer the list of things that you have to cancel. Like you can see up here, 7 and 3 are really far apart, and because of that, I was able to cancel the entirety of the 7 factorial, and it left me with not very many numbers. But 6 and 5 are really close together, so what's going to happen is I'm going to end up listing all the numbers down to 6, right? So here's 6 factorial. That's not going to give me a lot to cancel. Like that's kind of a pain. And then I'm going to get 5, 4, 3, 2, and 1. So you can either type it in as is in a calculator, but if you were truly doing this by hand, you would probably use some of these numbers on the bottom to cancel some of the numbers on the top, right? So I'm probably going to use the 4 and the 2 and the 1 to cancel the 8. I'm probably going to use the 3 to cancel the 9, right? And I'm probably going to use the 5 to cancel the 10. So what ends up happening is I'm pretty sure what I have left on top is an 11, a 2, a 3, and a 7, right? And I don't know what 11 times 42 is off the top of my head, so I'm going to end up bailing and using a calculator anyway, and I'm going to get that it's a 462, right? Because the 7 didn't cancel, the 2 and the 3 didn't cancel, and the 11 didn't cancel. So I can also do that by hitting second enter, right? And I'm going to go ahead and type in an 11. Notice I'll need to insert because I'm putting a 2-digit number, so second insert, put that 1, and then I'm going to put a 6 here. Hey, there you go. So same idea. All right, so after all that, it's finally time to talk about the stuff that this section covers. So a binomial experiment is essentially an experiment where there's 2 conditions that you have to meet. Number 1, the experiment consists of n number of trials, right? You have to have a certain number of trials, and each trial is either categorized as a success or a failure. There's no halfway. Either it worked or it didn't, right? There's no gray area, right? This is 100% success or failure, and the trials are identical and independent with a constant probability of success p. So what we mean by identical is, for instance, flipping a coin is a really good example of a binomial experiment. You flip a coin, you either get heads or tails. There's no gray area, you get heads or you get tails. So if we're saying that tails is a success and heads is a failure, then anytime I get tails, that's a success. Anytime I get heads, it's a failure, and that's it, right? They're all identical, right? They don't impact each other. My first coin flip doesn't have any impact on the second coin flip. There is a probability of p that I will get tails, right? Specifically, the probability is 1 out of 2 that I will get tails. There's a probability of 1 minus p, which would also be 1 out of 2, like 0.5, that I will fail and will get heads. All right, so that's a perfect example of a binomial experiment. If you have a binomial experiment, you can find the probability of getting r successes, right, in n trials, meaning you try 10 times, you want to see how likely it is that you get 6 successes by using this crazy formula. So the probability is n choose r, which is the notation we just went over, p to the r, where that p is that probability of success, and then 1 minus p to the n minus r. So let's go ahead and walk through this. I did intentionally put this formula on every page so that you don't have to memorize it. Remember, I'm not giving you a test on this. I just want to expose you to the material. So suppose that the probability a seed will germinate is 80%. Okay, so this is the probability of a success, right? That's p, which means that 1 minus p would be 20%, right? There's a 20% chance of failure. What is the probability that 7 seeds will germinate if 10 are planted? So n is 10, that's how many seeds you planted. You want to know what's the probability that 7 of them are successful. Well, the probability is going to be 10, choose 7, right? Because n is how many times you tried, and 7 is how many successes you want. The probability of success, which is 0.8, raised to the number that you want to attain, which is 7, right? And then the 0.2, which is the probability of failure, right? And you can write that as 1 minus 0.2, 1 minus 0.8 if you want, and then simplify it to 0.2. That's fine if you need that step. Let me just, so 1 minus the success rate raised to the 3, which is the other 3. So this is the probability of failure or of success. These are the ones that would fail. So if 7 succeed, 3 fail, right? And that's what I'm going to plug in. That's what I'm supposed to plug in to find my value. So the probability is going to be, and it's totally fine to use a calculator, right? So I am going to put the 10 NCR in parentheses, right? And the reason I'm going to do that is that I want to make sure it's clear that only that 7 is in the NCR. So 10 NCR 7, right? And then I need a 0.8 raised to the 7th, right? And then I need a 1 minus 0.8, or you could put that as a 0.2, raised to the 3rd, right? And if you're at all nervous about having the parentheses sitting right next to your exponent, you could do second insert, and you could put multiplication to make it clear that you're trying to multiply those things. That's fine. So I end up getting that there is a 0.2013 26 blah blah blah, keeps going, right, percent chance. So that's a 20.132 or 33% chance, right? So that's the likelihood that 7 out of the 10 of these would succeed, right? So I'm not asking you to memorize this formula, right? But there are a lot of experiments that do have success or failure, and that's it. That's not true of every experiment. In a lot of experiments, there are gray areas where something is slightly successful and you're trying to figure out a hypothesis to how to make something more successful. But there are definitely lots of trials that you can run scientifically and in things like computer science where something is either a success or a failure, and that's it. And so this is a good example of a way that you can calculate the likelihood that something will work, right? So, and just to point out, if you were trying to plant stuff, this might be a really good way for you to gauge how many seeds you expect to have to plant. If you know you need 7 seeds that are successful, you might be able to gauge how many seeds you actually have to plant in order to have those 7 seeds be successful. So, cool. All right, so we're going to try a P4 that is like E4. Again, the formula is down at the bottom. I don't need you to memorize this. Even if you end up in like a lot of stats classes, they don't make you memorize a lot of the formulae. They just make you know how to use them. So suppose the probability of a seed germinating is 85%. What is the probability that 4 of these seeds will germinate when 7 are planted? So 7 is my N, right? That's how many I'm planting. I want 4 successes, so that's going to be R. My probability that it's going to happen is 0.85, which means my probability that it's not going to happen, right, is 1 minus 0.85 or 15, right? So 15% or 0.15. So my probability is going to be N choose R, 7 choose 4, okay, so that quantity, times my P, which is the success rate, raised to the number of successes, right, times my not success rate, which would be the 0.15, raised to the number of not successes, right, which would be 7 minus 4 or 3, right? So I'm going to go ahead and hit second enter because I'm kind of lazy and I already entered the stuff in my calculator, and I'm just going to type over it. So I'm going to change the 10 into a 7 and then delete, right? I'm going to change the R that I had, which was 7, into 4. This is no longer a 0.8, it's now a 0.85, so I'm going to second insert and put a 5 to the 4 successes, right? And then I can either do 1 minus 0.85, or I could just make it a 0.15 since I already did the math on that, right? And that would be to the 3rd. And there you go. So my probability is approximately a 0.06166, right? Which would be a 6.166% approximately. Okay, so that's the likelihood that I have 4 successes out of those 7. All right. So example 5, a medical center has 8 ambulances. Given the ambulance's current condition, regular maintenance, and restocking of medical supplies, the probability that an ambulance is operational is 0.96, right? So 96%. Find the probability that at least 6 of 8 ambulances are operational. So at least 6 is tricky. So at least 6 actually means 6, 7, or 8, right? So basically, I'm going to find 3 probabilities here. I'm going to find the probability of 6, probability that 7 are good, and the probability that all 8 are good, and then I'm going to add those probabilities. So basically what's going to happen is I'm going to go ahead and find the probability that 6 of them are good, right? The probability that 6 of them are good is going to be 8 choose 6 times the 96% to the 6 that are functional, and the 0.04, because that's what 1 minus 96% would be, for the 2 that aren't. I'm going to find the probability that 7 of them are functional, which would be 8 choose 7, 0.96 to the 7th, and the 0.04 to the 1st, right, because 8 minus 7. And I'm going to find the probability that all 8 of them are functional, which will be 8 choose 8, 0.96 to the 8th, and then a 0.04 to the 0, because there aren't any non-functional. So I'm basically going to get 3 probabilities, and then I'm going to add them and say that it's all of those things combined. So I'm going to hit second enter, and I'm going to find each one of these at a time, and I'm probably going to store them because it's easier to store them. You also could type it as one big sum. So I'm going to do 8 choose 6, and then it's a 0.96 raised to the 6, and a 0.04 raised to the 2nd. All right, so I'm going to go ahead and store this as alpha A, right? So I'm going to say, hey, cool, this is approximately a 0.03506, 7 or 8, right? But I stored that as A, so I'm going to call that A. And then I'm going to go ahead and hit second enter twice because I want to get back up to that thing, and I'm going to change this to a 7 and a 7 and a 1, okay? And notice that that probability is 0.24046 3 da 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 da, and I'm going to store that as B, so store alpha B. So you might think it's odd that the percentage is getting higher, that 7 of them are intact, but again, notice how likely it is that the ambulances are working. So actually the low probability would be that they're broken in this case, so 96% chance that they're working. So what you're going to find is it's actually a much higher percent chance that most of them are functional, because that's the much more likely thing to be happening. And so it's very likely that all of them are functioning, right? So 8, 9, da 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 da. I'm going to store that as C, right? So we'll do stow as alpha C. And then the answer I want, so the probability that we're looking for is the thing I called A plus the thing I called B plus the thing I called C. So alpha A plus alpha B plus alpha C. You don't want to round answers till the very end, right? So it's going to be 0.99692, which if we put that as a percentage is 99.692%. So it's very likely that 6 or more of these ambulances are running, right? So again, what's tricky here is that this wasn't a single value. This wasn't the probability that 6 of them work. It was the probability that 6, 7, or 8 of them work, and that's tricky. All right, so let's go ahead and do one more, and then we're going to talk a little bit about how this works visually. So veterinary medicine, suppose that the probability of a sick animal recovering within a week is 70%. What is the probability that 4 out of 6 animals will recover in a week? So this one is back to being a little bit easier than this one was, because this one, notice that this was 6, 7, or 8. This one is just asking directly for 4, right? So what's the probability of 4? So the probability is going to be 6 choose 4, because there's 6 animals and you're choosing 4 of them. The probability of recovering is 0.7, so 0.7 times the number of successes. If the probability of recovering is 0.7, right, then the probability of not recovering within a week is 0.3, right? 1 minus 0.7, so 0.3 to the 2nd. And that's what I'm going to put in my calculator, right? So the probability is going to be, I'm going to go ahead and do 6 math over to probability 3, so 6 choose 4. And then we want a 0.7 to the 4th, and a 0.3 to the 2nd. Go ahead and enter, and I get that there is a 32, I don't actually have to approximate that one. That's not rounded the way it is right now. It is approximate when I move it to only 3 places. So 32.413 or 4% chance that 4 of the 6 animals will recover in a week. Okay, and so that's the last of our examples. I think the trickiest one was E5. So let's look really quickly at how this works with a graph. you can use a relative frequency chart to make a histogram of probabilities in a binomial distribution. So basically, let's say we flip a fair coin 6 times with the goal of getting heads, right? So heads is success and tails is failure, which is the opposite of what we said before. A binomial distribution using this, right? If it's a fair coin, right? If it's a fair coin, it is equally likely that I get no heads as if I get all 6 heads, right? So getting all tails versus all heads is the same likelihood, and you'll see how that's an even distribution, right? So it's symmetric, right? It's symmetric around the middle because the most likely thing that's going to happen is that I'm going to get half heads and half tails, because 3 heads would mean 3 tails, right? That's the most likely thing. It is slightly less likely that I would get a break of 2-4, right? 2 heads, 4 tails, or 2 tails, 4 heads. It is slightly less likely that I would get 1 heads and 5 tails, or 5 heads and 1 tails. And then it is the least likely that I would get all heads or all tails, right? And that's a standard symmetric binomial distribution. The reason it's symmetric is because the probabilities are both 0.5. That's why it's symmetric, right? Flipping a coin is a 50-50 shot. But when the probabilities of successes and failures are not equal, the binomial distribution obtained shifts left or right. It's not symmetric. So we actually saw some examples of that when we talked about a seed germinating, right, that there's an 80% chance that it will and a 20% chance it won't. Well, that's not going to be symmetric because it's a much higher chance that it will work than it won't. The success is a higher percent chance. So interestingly enough, so you'll just see that when you have a higher probability, so let's say, so a distribution that has a higher probability, let's say you have a weighted coin that tends to make you get heads instead of tails, well, that's going to be this distribution. It is more likely, if you look at this P, it is more likely that you are successful than that you fail, right? Since the probability of success is higher, you'll notice that the shift of the graph is that the higher values tend to be towards more successes. Where the probability of success is lower than a normal coin, well, you'll notice that the probability shifts and that histogram shifts to fewer successes, right? And so that's just kind of the idea of how this works. We're going to talk about a different kind of distribution called a normal distribution in 12.6, and that's the end of this video.